Video we are trying to show how the support vector machines, the main optimization problem is a convex optimization problem, and I will explain that. See, we said that we want to maximize 2 divide by mod w, which is the norm of the vector, the, remember, perpendicular to the hyperplane. Now this can be represent, if we maximize that, we can kind of reverse it and say that, okay, we rather want to minimize the mod w divided by 2, or half mod w, and for mathematical convenience we can write it as a half mod w square. We're subject to this constraint, you remember, the decision rule, and we are saying this is a convex optimization problem. Now, why we write it as a half mod w square? Because mod w is nothing but the Euclidean norm. Okay, mod w is square root of I got to 1 to n sum of all w, all the components of a vector. Now you see, because it's a square root, if we make it a square, then it's much easier mathematically to compute. Like the root mean square error, we always have calculated as mean square error in linear regression. Okay, so it's easier mathematically. So now we are kind of giving you a schematic of why it's a convex optimization problem. What is a convex problem? I would like to tell you, if there's a set and you pick any 2 points in the set with like A, B, and you connect them, and there's a line which is created, and that line, every point on that line lies within that set, then it's a convex set. So this is a convex set, but this is not, because in this case you can see, if we take 2 points and draw a line, this part of the line, the points on that line are outside the set. So this is not a convex set. Okay, given the definition, we are trying to show that see, there are mainly 2 unknowns in this optimization problem and this constraint. So W and B, that means the slope of the line and the bias or the intercept, those 2 are unknown. We are trying to calculate that. We have to find the best values for that. That's the objective of solving this optimization problem. But xi, which is a vector, and yi, which is a scalar taking values -1 and 1, they are known. Okay, so here w is a vector and b is a scalar, but SVM constraint, you can see that they are linear in the unknowns, they form a line. Okay, so linear constraints define a convex set. We have already said that these linear constraints define a convex set. So how to, one more time, the definition of a convex set: a collection of points in which the line, the line AB connecting any 2 points. So AB is in the set, it actually lies completely within the set. Okay, like AB here, what I give an example. So another mathematical example: if there is a set S, which is a subset of e to the power n, is convex, then it will happen if any linear combination of points is also included in S for all pairs of x1, x2. So this is a linear combination. This is a theta times x1 plus 1 minus theta times x2. Here we have to say that theta lies between -1 and 0. Okay, so theta can be 0, can be 1, or any fraction. Okay, so you see that I have shown this, why this happens, so with an example here. Let's say if ax1 equal to b and ax2 is also equal to b, that means x1 and x2 are 2 points on basically the same line, and x1 x2 belongs to a convex set, and let's say there is a constant k which is can take any value 0 or 1 or anything in between, and we can write it as a combination of points like k times ax1 plus 1 minus k times ax2. So this right side will also be multiplied by k, and when we simplify with the pure simple algebra, we'll find that this internal part, all the combination of points, a times kx1 plus 1 minus k times x2 equal to b. So this part is that is actually basically for any value of k, this will be all the points which belongs to the set. So that's why, because this thing can also be considered as a particular x, and then this satisfies this formula ax equal to b for any value of k between 0 and 1. So this set is convex. So that actually shows that if you take any 2 points and draw a line, and if the line lies within that set, this is a convex set. And this thing exactly happens for the support vector machine optimization problem, which is a convex optimization problem.